Start recording. Okay, so here's where it'll start. So of course where we ended was the string builder. Create a new string builder. For each thing, append to the string builder the string representation of the friend at index I, and a new line. You'll notice that on line 179, I think, where I just say, where I say builder.append, I don't say friend at index I dot toString. I don't go down here and say, where is string builder? Where's my toString? Here it is. I didn't write dot toString. I could. There's nothing stopping me from doing this. If I do this, it's entirely correct. It just so happens that the append method would do it for me. It's smart enough to know that, well, if you're giving something to a string builder, it wants the string representation. So you don't actually need to do it, but we do it there. But I did. To do it without a string builder, for those of you that are really, for whatever reason, very curious, I would say start with an empty string. I'm just commenting out. And then I would say s plus equals, which is the same as s equals s plus. You know what, let's do that. Friend at index I dot toString. And why not add the new line here for good measure? And then down here, return s. If I do this, and I run, I think if I did everything right, it'll look exactly the same. The functionality will be the same, it's just how it was implemented will be a little different. Friends. Let's try that out again. There we go. It looks exactly the same. Cool. I am going to go back, though, of course, to change it back to a string builder, because it's kind of the better way to do it. Run it again. There we go. There. Cool. Any questions about that? All right. Yeah. Okay. Equals and hash code. We'll start with equals. How do we define equality for a collection? This is a little different, because now we have two collections, just like we had, like with toString. We have a collection, which is really a group of other objects. And in order to generate the string representation of the collection, we use the string representation of the individual objects. So in order to check equality, we should also be checking equality based on the underlying objects within it. So the contact list equality check should incorporate the friends equality check as well. And there's a lot of ways we can do it. But Java provides a nice, easy way to go about doing an equality check on the contents of arrays. What I could do is loop through the two arrays, create a loop to go from 0 to size, and then check index 1 of this and index 1 of that, compare, index 2, 2, 3, 3, and so on and so on and so on. I could do that. But Java actually provides this nice built-in function in the arrays class, arrays.equals. And this will check equality on the contents of the arrays for us. And it actually includes a couple of nice parameters here. What this is saying is, okay, compare the array this.friends, starting at index size to index, starting at index 0 and going to index size, to that's friends array, starting at index 0 going to that's size. So this is just a shorthand way of saying loop over and compare equality on each of them. It's a nice, quick quick and easy way to loop it. To show you what I mean, if I go down here, I wrote the equals, arrays, I gotta import that. Alternatively, what I could do is say like, okay, for I guess I should also check if the sizes are the same if I'm doing it this way. I should say, okay, if this dot size is not equal to that dot size, return false, right? If the two contents have different sizes, they're not equal. I don't need to look anymore. They're not the same. Then what I can do is, okay, if this dot, really I should do objects, dot equals this dot friends at index I, that dot friends at index I. If not equal, return false. And then down here, I would just say like, okay, return true. If we ever get down here, it meant everything was equal. I think that would do the trick. I'm not going to bother testing it thoroughly, but that would probably do the trick. If not, hopefully at least gets the point across. This is the same idea, but you know what's easier to write? Just the arrays dot equals, right? Now, it's important actually in the way I just showed you that I compared the sizes first, because not only if the sizes are different does that matter, but imagine I didn't check the sizes, and contact list A had 5 elements, and contact list B had 6 elements, and the first 5 were the same. If I wrote my loop not smartly, I might end up comparing the first 5 and concluding that they're equivalent, while ignoring that 6th one and the other one, which would have been wrong, right? Anyways, comparing arrays dot equals, quite handy built-in function for us. Any questions about that one? All right. And last, we've got the hash code. So remember the whole point of hash code. First, again, I'm not going to go into great detail on hash code. It's outside the scope of this course, but the whole spirit of hash code is 2 things that are identical, are equal, must have identical hash codes. If they're different, we really want them to have different hash codes, but that's not always technically possible. Anyways, this hash code here, it says objects hash the size, and then add to the result each individual object in the array's hash code times 97 of the previous whatever. Who here knows why 97 is important? It's a trick question because 1, you don't, and 2, it's kind of just a trick. There's some fancy math behind it, but 97 is a prime number, and it happens to be a really good prime number for helping to ensure uniqueness when doing hash codes. It's not this not on the test type thing, it's just an interesting little piece of trivia. Yes?
Would it always be 97, or would you ever change that number?
There are a couple of other prime numbers that tend to be commonly used.
But stick to 97.
Yeah, you could do 97. IntelliJ will actually try to generate a hash code for you. And look, it did, but it wanted to use 31, right? By the way, this hash code isn't going to work great because of the contents of the array. This is going to hash the whole thing of the array, even though, anyways. The auto-generated one wanted to use 31. Does it matter? Nah. Someone asked me in lab, I don't remember who it was, so raise your hand if it was you. Maybe it wasn't in lab. They're like, yeah, but 97 is also the same, the integer 97 is the same binary as the character A. I remember you talking about that. Who was that? Someone said that. Maybe they're not here today. Someone observed that the integer 97 is the actual ASCII value of the character A. Remember with binary, 0, 1, 0, 1, 0, 1. The pattern of zeros and ones that decodes to 97 as an integer. If you decode it as a character, it's the letter lowercase a. Pure coincidence. It's not meaningful in any way. But someone did make that observation. I was really impressed that they remembered. But it doesn't matter. Yeah. Okay. Warning. Yeah. So I did include the contact list test class. If you really care, we can open it. There's a lot going on with the unit test for the contact list. I'm not going to go into this. If you really want to go for it. Have fun. I'm going to not talk about testing collections until we finish talking about the array stack, because the array stack is far simpler of a collection than the contact list. It's actually kind of funny. We spent 161 learning about classes, and then we learned about collections like data structures. And then we're starting this by re-implementing one that we did in 161. Turns out, this style here, this contact list one, is actually a rather complex collection. Once we hit the next collection that we're going to implement, we go simple. We simplify way more. So just FYI. And here's some code that you could copy paste to play around. I'm going to do that. Oops. There. In here, assuming I did copy everything over, I add a bunch of friends, I print out the friends, I remove a friend, I print out the friend, I clear, I print out the friends, there. So there we go. Now notice, interesting, the order, the first print was Bob, Jane, Clarence, Sandy, Adam, Adrian. But the next time I printed it was Adrian, Jane, Clarence, Sandy, and Adam. What's up with the order? Why did suddenly Adrian come first? Anyone know? This is not a trick question. If you're paying attention, you should know.
The way that we designed the remove was to take the last one and replace it with one movement.
Exactly. The reason the first one got replaced is I just so happened to say remove Bob, who was at the beginning. And then the remove always put whoever was at the end to replace wherever they came from. If I go back here and change this to, let's say it's Clarence Cartwright, that's getting cut, tree lover, 1523. And we rerun it, we should see Adrian pop up to wherever Clarence was.
Give an extra bracket, I think.
I've got an extra parenthesis. Good catch. Those are parentheses, not brackets.
Yeah.
Come on.
I know, big fan.
How dare you mix those up like every other human? So Bob, Jane, Clarence, Sandy, Adam. Bob, Jane, Adrian, Sandy, Adam, right? Just FYI, a bracket is the square ones. Those are brackets. The round ones, the curved ones are parentheses. And then the squiggles are called braces, but I greatly prefer squiggle. I mean, why wouldn't you use the word squiggle if you had the chance? Come on. You know I'm right. Okay, any questions at all about that collection we just made, the contact list or collections in general? All right, seeing none. So, now we can finally start this course. Now we can finally start talking about 162. So welcome to 162. Everything up until now, the last 3 weeks have been purely review. FYI. Obviously I'm being a little silly because there was some Java you got to jump into. But it was review. Now we can start 162. Collections. The whole point of this course is data structures and algorithms that we use with these data structures, but the emphasis is on the data structures. So collections. Collections and abstract data types. A collection is a group of things that are be treated as some special cohesive computational unit. And in computer science, we have a couple of very popular elementary collections that we use frequently. Stacks, queues, bags, lists, trees, and graphs, and dictionaries. I don't know why dictionaries maybe should be there. And the list there is far from complete, but those right there are a big part of early computer science. When I say, I want to be careful though, because when I say elementary, and when I say, oh, they're the ones you're starting with, that's not to mean they're trivial. That's not to mean they're not important. These are very important. Maybe stacks right there might be the most important. Arguably, with 2 stacks, you can do literally anything. But we're going to start with stacks too, but they're very important, not trivial, just we start with these. And for the most part, we're going to focus on linear data structures. The first 3 big data structures we're going to learn about are linear, and then we finally move to a nonlinear one at the end of the course. Linear data structures are those that you can kind of draw a straight line with. Like there's a beginning, there's an end. If I ask you, if I give you a linear collection and say, okay, put your finger here, and I say what comes next, there's an answer. Right? Linear. Nonlinear perhaps makes more sense with an example. But the first one we talk about is a stack. Who's ever seen a stack of things ever? Put up your hand. Maybe it was a stack of plates. You ever go to a buffet where they've got those like funny stack of plates thing? Right? Or even if you open your cupboard. Who has a stack of plates in their cupboard right now at home? Of course. And if you go to take a plate, if you're a normal person, where do you take the plate from? The top. And then let's say you washed a single plate. Where do you put the plate? On the top. Who puts it on the bottom? Weird people over there. You don't do that. That's a weird thing to do. All of the action on a stack happens at the top. A queue. Who's ever stood in a line before? Of course you have. When you enter a line, where do you go if you're a normal human that lives in society? The back of the queue, right? You don't just jump to the front of the queue. You're going to piss a lot of people off if you do. So the rule is you enter the queue at one end, and you wait your turn. Eventually you work your way up to the front, and then it's your turn, right? So entering happens at one end, and removing happens at the other end. The stack was different. Entering and removing always happened at one end, the top, and a queue is different. It has like a front and a rear. Then we have bags or lists. Sometimes we can kind of think of them as the same thing, but a bag is just some more general collection of things. Maybe we can add and remove to the beginning, middle, end. Maybe there should be some rules around the bag or the list, depending on the type. For example, this is an example of an ordered bag, where the elements must be ordered based on some ordering. The elements themselves define the ordering. Here it's the integers. And if I say, add the number 58, where does it go? Well, if this was a stack, you would just put it to the top. If this was a queue, you would add it to the rear. If it's an ordered bag, though, like a sorted bag, well, you need to add it such that the order of those elements is preserved. Like, I can't add 58 before 51 because that would break the rule. So there's a more general version of a linear data structure there. But then we have nonlinear data structures, and the first one might be something like a tree. Everyone jokes computer scientists are weird. They draw their trees upside down. Whatever, fine. But you can think of, there's a lot of things humans like to represent as trees. Anything that has any form of hierarchy is a tree. Trees are everywhere. Who here has a textbook in their bag right now? If you were to open it and look at the table of contents, believe it or not, the table of contents is going to be sorted like a tree. You've got the thing at the top, that's going to be like the main page. And then you look at all of the different chapters. And then the chapters have subsections. And then there's subsections in the subsections and so on. If I go here, the same thing is true here. Here's like the root. And then collection is a chapter. That is a sub-node. And then in there, I have a subnode called collections and ADTs. And then in there, I have sub-subnodes called linear and nonlinear. So anything that could be represented as a hierarchy is a tree. A file system on your computer, wrong one. A file system on your computer also could be representing a tree. They're everywhere. And then an even more general version of a tree is a graph. And I know you always hear graph. I hate to tell you, you have been misled since you were this big. I know when you think of graph, chances are what you're really thinking of is a plot. But for whatever reason, your teachers have been lying to you and they've been calling everything a graph. They're plots. Okay? A graph, that's a graph, right? You've got nodes and edges. Nodes are things, entities, and edges are some relationship between them. So this example, I've got airports, hypothetical, flights between them. If I want to go to New York from Moncton, no, I can't take a direct flight. I got to go through, looks like the only way you get to New York City is through Halifax, I guess, right? So there we go, right? Whoever's taken a flight before, whoever had to book their own flight, then you have options of like airports and whatnot. Yeah, it's a graph. Now, the graph is a representation of that information. I mean, connecting flights in and of themselves is not intrinsically a graph, but we can represent it as a graph quite nicely, right? And what's nice about the graph too, you could kind of represent it spatially, which this kind of is trying to do, right? Now, before when I said linear, a graph would be an example of a nonlinear. A row of students is linear. If I'm looking at you and say, who comes before and after you? Point. There you go, it was obvious, right? But let's say you're pointing at Buffalo. And I say, what comes before Buffalo? You go, that doesn't really make sense. What do you mean before? What comes after Halifax? Your response is going to be, well, what do you mean? Which is the correct response. Because maybe there's a way for me to define an order on these things. But with the linear data structure, there was no mystery. You didn't need to ask a follow-up question, did you? You were just like, there. Graph, it's complicated. Those are nonlinear data structures. Yes?
Where else would you see a graph other than airports and picking your flights?
Everywhere. Graphs are everywhere. A social contact network. In this room, are there people in this room you would consider your friend?
Sure.
All right, consider the students in this room nodes, and edges are like friend relationships. A graph can represent whatever the hell you want it to. A graph can represent a maze, which you're going to do in this assignment 2 and 3 for this course. A maze, where each node is like an open cell, and an edge is, well, this cell connects to that edge, right? Graphs are everywhere. They're very general. They're fantastic. We love graphs. But they're complicated. So we work our way up to that. We don't touch graphs in this course. We only do it incidentally through assignment 2 and 3. So you want to do graphs, though, because they're fun.
I want to do trees. I don't know, man.
What?
Oh, it's over. I want to do some trees. Yeah.
All right, fine. Well, you get to do trees.
Thanks.
So, abstraction. The whole point of all this was, look, the airports aren't intrinsically a graph, but we can represent the airports and the relationships to one another with a graph. It gives us a nice way to abstract these relationships with this beautiful representation, right? Abstraction is something we do in everyday life. And it often is used in a nice, helpful way where we separate the what from the how. Okay? What can I do with it, and how do I do it? I use this example all the time. I don't need to know exactly how all of the parts, all of the underlying mechanics of my internal combustion engine, the brake system, the hydraulic system, and everything in my car, I don't need to know the how. All I need to know is the what. What can I do with the car? I get in, I turn it on, put it in drive and go. Right? I don't need to know the how. And we do this in our lives all the time. Right? Every system we interface with. And I use the word interface because you're going to think, oh, he's really working hard to use these computer-y sounding words. No, the word interface means how we interface with something, the what. What can I ask you to do? Right? The how is, well, how you do it. Think of like a boss telling their employee, go do this. And they're going to go, how? The boss is going to be like, I don't give a shit, just do it. Right? I don't care how you do it, just do it. Solve the problem. Right? Every aspect of our life, we're always dealing with these abstractions. We separate the how from the what all the time. It's an important feature of our existence. So what we can do, how it's actually done. One may know what they need to do to drive a car, but they don't know how the car does what it does. And that doesn't really matter. Like lists in Python. Who here opened the hood and looked at how lists work in Python? No, you didn't. But it didn't matter. You never needed to open that hood and look at how lists did what they did. You just needed to know what they could do for you. Right? That's all that mattered. And that's a huge part of programming. We go out of our way to generate these abstractions of black boxes, where the black box is a way for me to say, I've got this thing that I can put stuff in, get stuff out, and I know what it can do for me. How it does it, I don't care. And we do that because it makes our lives easier and better. So we do this all the time. So the above ADTs, abstract data types, we ADT. A stack, it's not a type. There's no it's not like an integer, right? But it's more of an abstract collection of integers. So we call them ADTs, abstract data types. So what we can do with an ADT, like a stack? Well, I can add things and remove things. How does that work? I don't care. I just want to be able to add things and remove things. Now, having said all that, we are talking about, one, this is a course on how a stack works. And I just made a big rant about, we don't care about the how, we care about the what. Really what we care about is separating the how from the what. That's the important part. We're going to build the how because we have to learn how to do that. And having done that, we want to make sure we work really hard to separate the how from the what. So this is, earlier in the semester I said, this is what sometimes people will say is you're working on both sides of the interface. The interface is like the definition of the what. You use the list, what you can do with it, and you used it. But how did it work? So we're on both sides of this interface. And that's by design for this course. All right. Layering, right. So if systems are large, we start to have multiple levels or layers of abstraction. If this is the case, one may want to group components and restrict how other layers of abstractions interact with one another. This happens intrinsically by default in real life. Systems just develop like that. But when we are designing them, we might want to have some control. For example, when we made our methods private, we kind of give some control and restriction over how certain things are used and interacting and how they can be interacted with. Right? So we do this in real life. If I say, tell me how to cook pasta, chances are you're going to tell me in a rather abstract high-level layer. Boil some water, add some salt, add some pasta, wait a couple minutes, and you're done. And then if I say, no, more detail. And you go, okay, fine. Get a pot, fill it with water, put it on the stove, turn on the stove. And we can play this game forever. No, tell me more detail. All right. Locate the pot. No, more detail. Open the cupboard, find the pot, right? We can do this forever. There's a lot of layers in there. We, by just existing, get really good at this. And it's kind of funny how a lot of times in computer science, there are things we do in everyday life, but as soon as someone says, okay, try to formalize those instructions, it gets kind of weird. Try to formalize how you generated these layers of abstraction. You're like, well, I don't know, I just did it. Go back to 161 when I said, have you ever sorted anything ever in your life? Of course you have. And if I ask you, well, how did you do it? You're left going like, I don't know, I just did it. And it's kind of funny when I put you on the spot and you have to go like, okay, what the hell did I do? And you're trying to formalize those steps to get them into an algorithm. It's kind of funny how we're naturally good at it, but sometimes when you're asked to do it, you're kind of like, oh, I don't know. Right? I always kind of find that peculiar. All right. Yeah. Turtles all the way down. Anyone ever hear that expression before? Whatever. It's an expression. That means like, you can always keep going. Turtles all the way down. Anyways, whatever. It doesn't matter. I could play this game with cooking pasta to neurons firing in your arms. or ion pumps moving ions that are charged to help the neurons. Thank God there's layers of abstraction, several layers of abstractions between me having to worry about ion pumps and making spaghetti. Right? There's a lot of layers of abstraction. That's a good thing. But at the end of the day, someone or something had to care about ion pumps. Right? Kind of funny to think about, but okay, data structures. The data structure is an actual implementation, concrete implementation of an abstract data type. So we have this idea of a stack. All adding to the stack happens at the top, all removing from the stack happens at the top. But how do we implement that? Well, an implementation is what we call the data structure, the actual data structure. Though I will say it is remarkably common to mix those words up. A lot of times people will just say data structure is kind of a catch-all. I'm probably going to do it. You're going to do it. Everyone does it. But there is a difference. Yeah. And there's the warning about data structures being used as a catch-all term for both the ADT and any implementation. So this is just a review of topic 1 of this course, which was basically all this. Stacks, queues, lists, bags, trees, graphs, what, how. And again, to really re-emphasize, I know I put a big emphasis on the what, not the how, but really what I'm doing is putting an emphasis on separating the what from the how. We care about both, but it's good to separate them, because if you separate them well and cleanly, you've created a nice good layer of abstraction. This idea that I just talked to you about, it's going to make a lot of sense. If not already making sense to you, it's going to make a hell of a lot of sense once we get to topic 11. Things are really going to click there. But until then, we'll still have a lot of fun, I'm certain. Okay, any questions about that? Yes?
Is there a best one?
A best data structure? No. Okay. That question can be interpreted in different ways. The answer is no. There's no like silver bullet. They all have pros and cons. You use a certain tool for certain jobs. And if you have a different type of job, use a different tool. Right? So these are just more tools to your tool belt. The tools we've learned in 161 were your if, your variables, your types, your loops, right? Those are those tools. Now we're building more advanced tools that we're just adding to our tool belt. And the problems that we have, we pick the right tool for the job. And depending on, maybe there are 2 tools that could work for the job, but depending on which one you pick, it kind of affects how you go about solving the problem. That said, with a general purpose list, you could treat a list as if it's a stack and a queue. A list is a generalization of both those things. And a list is a list, it's just more general. So you could use a list to do all the work a stack could do. You could. But we don't, because you always want to make sure you're not, we like to restrict the resources we're using. We like to restrict the interfaces because the choice of an interface kind of communicates to other programmers like, I picked this tool for this job, and here's why. So the code kind of like is self-explanatory. But once you have a list, a tree is a generalization of a list. A list always has one successor. A tree has multiple successors, multiple children. And then a graph is a generalization of a tree. A graph is like a tree, but it could have multiple parents. A tree, each thing can only ever have one parent. A graph, now you can have multiple parents. Now there's no idea of a parent or children, you just have things connected to everything. So you could use a graph to do anything. You could use a graph as a queue. Don't, but you could. So if that's how I interpret the question, I could say, well, the graph is the best because it can do everything. But you don't grab that Swiss Army knife to solve, right? To eat your spaghetti. Wow. Any other questions? That's a fun question. All right, jumping into the stack. Stack is a linear collection of elements. You already know what a stack is. It's a pile of things. All the action happens at the top. Adding and removing happens at the top. The word top is the key word here. Everyone uses the word top to mean the end of the stack we care about. And given this, sometimes, although you don't really hear this that often, but when defining it, people say this is a LIFO data structure. The last thing that you added would be the first thing to get removed. The thing at the top, if I just put a plate on the top of the stack and someone comes along and wants a plate, they're going to take the one that I just added. The plate at the bottom is the one, like if I added 10 plates and 10 people came to grab a plate, the first one I added would be actually like the last one that would get removed. So examples of stacks. Stack of plates. Web page history. Who's ever hit the back button on your website? Who's ever hit undo in your word processor? It's a stack. Every change you make gets added to the stack. Every time you hit undo, you remove the top thing. And you put yourself in the state you were right before. Undo, 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 undo. New website, new website, new website, back, 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 new website, new website, new website, back, 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 new website, new website, new website. Right? That's a stack. A call stack. That's how your computer works. But we'll learn about that later in the course. So here's a stack of colorful plates. I've got the bottom, I've got the top, but I added something there. That really dark teal, what color would you say that is? Anyone better with teal?
Yep.
All right, I'm proud of myself. Not cyan, no? I'm showing off. I know teal and cyan is like hues of blue. I know. So, if I added one, well, that's the new top. Adding something to the top of a stack is traditionally, and we will use this word, we use the word pushing. You push something to the stack. When you remove something, we call it popping from the stack. So we push and we pop. If you go back like 70 plus years ago, they didn't use the word stack. They used the word called like a push down, just as a neat history lesson, but today we use the word stack. And a stack is a very simple data structure that you can use to solve various problems, like history for your web pages that you're visiting, undos, right? In general, for the collections being discussed, including the stack, we're going to need a way to add something, remove something. Then there's this thing where we can look at something but leave it. We don't touch it, we just look at it, but we leave it where it is. We also want to check if it's empty or not, and we want to know how many things are in that collection. So those are the core 5 things we care about for all the collections we're going to write. A way to add, a way to remove, a way to like peek at it, a way to check if it's empty, and how many things are on it. I suppose you could say, well, empty is kind of redundant if you have a size, but whatever. We'll do that as well. Because if the size is 0, that means it's empty. But we'll do that anyways. However, the way that we do the adding, the removing, and whatnot will differ depending on what the data structure is, what the abstract data type is. If it's a stack, we do it one way. If it's a queue, we do it another way. So when focusing on a stack, we say push. Well, that's adding something to the collection. And the element that was added becomes the new top of the stack. Then we have pop, remove an element from the collection. The removed element comes from the top of the stack, but it's removed. So the element that comes after is the new top. And yeah, then that element is like it's gone. It's not in the structure anymore. The removed element will be from the top, yeah. Okay. And then peek. Return the element at the top of the stack, but leave it alone. And peeking doesn't alter the state of the stack at all. We just looked at it, okay? We just observed it. And then if you're saying like, well, why can't I access something from somewhere that's not the top? Why can't I access like the third thing? I'm going to say, look, if you want to do that, then you're not using a stack. You're using a list. Okay? Yeah, but I really want to do it. Then use a list, great. If you're using a stack, this is all you get. That's it. And then you're going to say again, but what if I really want? Then don't use a stack. The definition of a stack is that. Push, pop, and peek. Size is empty. If you really want to do something more, then don't use a stack. And that's fine. Maybe you really don't have to use a stack in that situation. Sounds like you don't if you really want to access that third thing. So, now, push, pop, peek, size is empty. That is the what. At no point have we covered how we implement this thing. It's just the what we can do with it. Further, this push, pop, and peek had nothing to do with Java, had nothing to do with Python, has nothing to do with C# or C or C++. It has nothing to do with a programming language either. It's just this abstract idea. We can push things, we can pop things, we can peek, get the size, and check if it's empty. We never talked about the how. We will. We never talked about the how because it doesn't matter yet. Nor does the programming language either. It will matter when we actually go to implement it, which is the next topic. But that's it. It's just the what we can do with it. And we'll stop here and we'll pick up with the example use tomorrow.